The question I have is, could you tell us about dimensions and units? Dimension can be described in a number of different ways. This is one way. Dimension is a property of a variable or quantity that can be measured. A unit, on the other hand, is a specific numerical value that is assigned to a dimension in accordance with a specific system. In mechanics, there are 7 primary dimensions. The primary dimensions are also sometimes called the basic dimensions. The primary dimensions are independent dimensions. In other words, each one in this list is independent of the other. So what are they? They are the mass, length, time, temperature, electric current, amount of light, and amount of matter. To perform what are called dimensional analysis and to refer to them in a very unique way, we use specific symbols. These symbols, of course, vary from book to book and discipline to discipline and professor to professor and so on. Here is one set that is most commonly used. Capital M for mass, capital L for length, little t for time, capital T for temperature, I for electric current, C for amount of light, and little n for amount of matter. Not all of them are relevant to all mechanics courses. In statics, we will be mostly dealing with mass, length, and time. And when you move into the follow-up course called Strength of Material, you will also be dealing with temperature, because there we talk about thermal effects like expansion, shrinkage, and so on, and the temperature comes in there. While the 7 dimensions we discussed in the previous slide are the primary dimensions, dimensions of other quantities like force and velocity can be derived by combining these primary dimensions. And these derived dimensions are called the secondary dimensions. Depending on the subject that you are studying, you're going to run into many such secondary dimensions. Here are 3 examples: force, velocity, pressure. Since the quantity force forms the basis of pretty much everything we do in courses like statics, dynamics, and strength of materials, we include that along with mass, length, and time and call this set, there are 4 of them here, as fundamental quantities. But of course you should remember the first 3 are the primary or independent dimensions, and force is a secondary dimension or derived quantity. Now let's talk about units. There are a couple of different systems out there. The 2 most commonly used unit systems are the International System, also called the SI system, and the US Customary System, abbreviated as USCS. Within each of these systems, there are several units that are used to measure these fundamental quantities. For example, length can be measured within the SI unit system using millimeters, centimeters, meters, kilometers, and so on, right? So what I have listed here are the primary or standard units. In the SI unit system, we use kilograms for mass, meter for length, second for time, and Newton for force. I'm going to define what exactly Newton is in a second. And in the USCS system, the unit for mass is slug. Again, I will define that in a second. Foot for length, second for time, and pound for force. So we do note that we use the same unit for time in both systems. And here are the conversion factors. Very often we have to go from one system to the other. Alright, now let's talk about some of these units that you are probably not familiar with, like slug. We already talked about Newton's laws, right? So we use the second law, remember F equals ma, in order to relate force to mass. Let's first go ahead and define the dimension of acceleration. Acceleration is one of the derived quantities, right? But I'm sure you recall the definition of acceleration, right? Acceleration is distance divided by time squared. In terms of the symbol, the dimension of acceleration would be L over t squared. The distance has a dimension of length, and the symbol for that is capital L. and time, of course, has the symbol of little t. Now, if we use the standard unit for each of the two dimensions in this expression, in SI unit, the unit of acceleration would be meter divided by second squared, whereas in USCS system, it will be foot divided by second squared. Now, if we go back and take this F equals ma equation, we can find the relationship between units of force and mass. In the SI unit system, if I express the mass in kilogram and the acceleration in meter per second squared, the resulting force is what is called Newton. In other words, 1 Newton is 1 kilogram multiplied by 1 meter per second squared. Another way of saying that is that if I take 1 kilogram mass, right, I need to apply 1 Newton force to it in order to make that accelerate at 1 meter per second squared. Similarly, in the USCS system, if I express the mass in slug and acceleration in feet per second squared, the resulting force is what is called 1 pound. In other words, 1 pound equals 1 slug multiplied by 1 feet per second squared. Although in the SI unit system, the usage of kilogram and Newton are equally common, in the USCS system, it's not very common to use slug, right? We usually use pound for force, and nobody knows what the unit of slug is, right? But now you know, this is what slug is. Well, hopefully at this point, you guys have a pretty good idea of the definitions of dimensions and units and the difference between the two. When we deal with dimensions and units, another useful thing to know in the SI unit system are the prefixes. I'm sure you are familiar with most of these. For example, 1 kilometer is 1,000 meters, right? Well, here's a partial list presented in a systematic way. The first column lists the multiples, and the second column lists the multiples in exponential form, and the third column lists the prefixes, and the fourth column lists the standard symbols that we use. And in the final column, I am presenting you an example involving the dimension of length. Starting from this row, which represents the standard unit, as you go up, the multiple increases. So 1 kilometer is 10 to the 3 meters, and 1 megameter is 10 to the 6 meters, and 1 gigameter is 10 to the minus meters. And as you go down from this row, it decreases. So 1 millimeter is 10 to the minus 3 meters, 1 micrometer is 10 to the minus 6 meters, and 1 nanometer is 10 to the minus 9 meters. If you're wondering if there's anything this small, thickness of a clay mineral called montmorillonite is roughly 1 nanometer. What about up here, right? The distance between Earth and Moon is 384.4 million meters, and that is 384.4 times 10 to the 6 meters, and using these prefixes we can write that as 384.4 megameters, right? A lot more convenient than writing like this.